This is section 18.6, and in this opportunity we will talk about the relationship between the Gibbs free energy and equilibrium. Up to this point we've been discussing of our equilibrium, and we've been talking about whether a reaction is spontaneous on the forward or reverse direction. And well, our measure of spontaneity is the Gibbs free energy. If it's negative, then it's a spontaneous process. If it's positive, then it's a non-spontaneous process. And the one thing that you have to remember is that non-spontaneity doesn't mean that the process will never occur. It's just that you have to provide some sort of intervention for that process to occur. And as an example, in this picture that you see in the background in this slide, this is actually an inverted waterfall. And what is an inverted waterfall? Well, the water is actually flowing upwards, right? And why is the water flowing upwards, you may say? So it's because there is wind coming this way and pushing the water up. So does the water flows upwards spontaneously? No, it doesn't do it. It will flow downwards spontaneously. Can it do it upwards? Well, you have to provide some sort of intervention for that to happen. In this case, the wind is providing that intervention, and then you see water flowing in the opposite direction. Okay? Well, probably not very chemistry related, but I think it proves the point that a process that is non-spontaneous doesn't mean that it will never happen. Okay? It will happen provided the proper intervention. So this is all about calculating delta G at non-standard conditions and how the equilibrium relates to those conditions. Okay? Up to this point, we've been talking a lot, or we have been assuming that we've been working under standard conditions. And just to remember, standard conditions for all practical purposes are a temperature of 298 Kelvin, a 1 molar concentration for solids and gases at 1 atmosphere. Now I want you to think about this, right? If you are under standard conditions, it means you have to comply with those requirements. Now think about calculating a K, right? For as simple a process is A goes to B, right? K equals concentration of B over concentration of A, right? Under standard conditions, it means the concentrations has to be equal to 1. So this is 1 over 1. It means that under standard conditions, K is equal to 1. And that's going to be the case regardless of the stoichiometry of the reaction, because if all the concentrations and all the pressures or anything that you use in the expression is equal to 1, well, 1 raised to any power is going to be 1. And the constant is going to be 1 under standard conditions. Okay, now let's write that down. Under standard conditions. Okay, because we are setting those values, pressures equal to 1 atmosphere and concentrations equal to 1 molar. Okay, the first equation that we're going to mention here is delta G equals delta H minus T delta S. You are already familiar with that. Okay, so remember delta G, if you talk about delta G standard, you are referring to precisely those conditions: 298 Kelvin, 1 molar, 1 atmosphere. If you are working at temperatures different from that of standard conditions, then you use this equation. Okay, that is assuming that delta H and delta S do not change with temperature, which is not entirely true, but to make things easier, well, we assume that that's the case. So if you want to calculate delta G at different temperatures, you use that equation. Now, if you have a different set of conditions, and by that you mean different from 1, concentrations different from 1, okay, or pressures different from 1, then we use this equation. Okay, think of this in terms of an adjustment that you do to delta G. This is your delta G standard. Let's write it down. This is delta G standard. And this is sort of a correction that you do because of conditions different from standard. Okay, and that's the Q. That's the Q that you have already that you already know. That's Q equal the same expression of K, except that you can use any concentration there. You can calculate delta G for any reaction under any condition. These also involve different temperatures, so you can basically throw everything at that equation. Far from standard conditions, far from 298, far from 1 molar, far from 1 atmosphere. So you can use that and calculate delta G under those particular conditions. Now at equilibrium, then delta G is going to be equal to 0. Not the delta G standard, the delta G for that reaction under those conditions, the condition of equilibrium, is going to be equal to 0. At that point, if you are at equilibrium, you have been calculating the reaction quotient already. At equilibrium, the reaction quotient is equal to the equilibrium constant. So we just take this equation, we make this equal to 0, which is what we have here, and then we end up with an expression in which delta G standard plus RT logarithm of K is equal to 0, right? Which means now we have an expression that relates delta G with your equilibrium constant. Okay, as written right now, that's the delta G standard, but you can apply that equation to any condition because temperature here is what is setting the condition, okay? And whatever equilibrium concentrations you have at those conditions. So that's gonna be the delta G under equilibrium conditions. All right? So that means we have to relate now when it comes to spontaneity. All right. So this is the relationship between delta G and the equilibrium constant. If you have the equilibrium constant, you can calculate delta G. If you have delta G, then you can also calculate the constant. And this looks like something that you're familiar, right? This looks pretty much like the Arrhenius equation with activation energy. Now, because you are working with energy, then the R that you use here is a 314 joules mole Kelvin, and that's going to be the case for most of the things that we are going to do here. Okay, so what do we have here? So now we want to determine here what is the relationship between delta G and K in terms of, well, if K increases, what happens to delta G? If delta G increases, what happens to K? And what does that have to do with spontaneity, right? So when delta G is less than 0, and this is negative, our measure of spontaneity is that delta G equal or less than 0, negative delta G. This is a spontaneous process. All right, and spontaneous process. Now, if we go back to our generic equation, equilibrium equation, okay, now incorporating the concept of spontaneity with delta G and K, well, a delta G negative for the reaction as written means that the reaction is spontaneous in the forward direction, right? If delta G is negative, and that corresponds with a high value of K. If K is large, products are favored, and you say that the reaction is spontaneous in the forward direction, or you also say the forward direction is favored. Okay, when delta G equals 0, K is equal to 1, and that represents the equilibrium at standard conditions, pretty much. Okay, so this is standard conditions. And when delta G is positive, larger than 0, then the process is non-spontaneous. Correct? And that represents a small value of K. Not a negative value of K, not a value of 0, but a very, very small value, much less than 1. Okay, so in that case, this is delta G negative, delta G positive, then if we have the same equilibrium here, then means K is very, very small, and then the reverse reaction is the one that is spontaneous. Okay, spontaneous in the reverse direction, it's non-spontaneous in the forward direction. Okay, and that's represented with K very, very small. So what is the meaning of all of this? Well, delta G, we have already determined that for delta G negative, the process is spontaneous, but now, since we're working with equilibrium, what it means is that the forward reaction is spontaneous, the reverse reaction is non-spontaneous, and that's represented by a value that is larger than 1. Okay, here in this case 1 represents standard conditions. Okay, if K is larger than 1, then the products are favored, in delta G is negative. Again, forward direction is spontaneous. Okay, your delta G is going to be equal to 0 at equilibrium. Q is going to be equal to K, and since you are at equilibrium, there is no favor reaction, and then you are at equilibrium, right? So therefore there is no net gain for the forward or the reverse direction, or forward reverse reactions. Delta G positive is non-spontaneous forward. Okay, here was spontaneous forward. And then we have a value of K less than 1. Okay, pretty much what this says is that K is larger than 0 but less than 1. Okay, and K could be very, very small. Okay, now how do we apply all of this? Well, we have this reaction, right? And we want to calculate delta G under several conditions. And the first, we want to know what is delta G under standard conditions. Okay, and what do you need for that? So how do you calculate delta G under standard conditions? And then you might be thinking, okay, this is gonna be difficult, right? Well, no, delta G under standard conditions is exactly the same thing that you've been doing for quite some time now. So delta G of reaction, if you are under standard conditions, you are using delta G standard of formation. Okay, so which means you need delta G of formation for carbon monoxide, you need delta G of formation for methanol, and technically you need delta G of formation for hydrogen, right? But hydrogen is an element, so this is equal to 0. Therefore, to calculate delta G of reaction based on your reaction here is going to be simply the delta G of formation of methanol minus the delta G of formation of carbon monoxide. Okay? Well, this is the lecture, so I have the values. If you were working this in the exam, you will have the values. But the delta G of formation for methanol is equal to minus 162.3 kilojoules per mole, and the delta G of formation for carbon monoxide is minus 137.2 kilojoules per mole. So when you complete this calculation, you end up with minus 25.1 kilojoules per mole. Now this is pretty much, well, it's not specified here, but this is the delta G standard for the reaction. Okay, so it's delta G under standard conditions for that reaction. All right. Now what do we have at equilibrium? How do we calculate this delta G for equilibrium condition? Well, this is where we use the equation that we have already expressed before. Delta G of reaction under equilibrium conditions is going to be minus RT logarithm of K. And I forgot to add the value of K here. Kp is 226 10 to the negative power 4, and this is at 25 Celsius. Okay, sorry about that. Was it here? No. So that's the value of the constant. I just forgot to add it in the slide, and we are using this equation because that relates the delta G for the reaction under equilibrium conditions, because you are using the equilibrium constant. So delta G of reaction is going to be minus 8314 joules mole Kelvin times the temperature. We are doing this at equilibrium at 25, because that's the condition that we have, and 25, right, is 298 Kelvin times the logarithm of the constant, which is 226 10 to the power 4. Okay, so under equilibrium conditions, then the delta G is going to be equal to, remember that you have to, well, you cancel Kelvin with Kelvin, and you will obtain about minus 24,800 joules per mole, which is pretty much minus 24.8 kilojoules per mole. Okay, once again, this is under equilibrium conditions. Whatever pressures or concentrations you are using for equilibrium here, okay, has to be equilibrium concentrations, equilibrium pressures. But if you don't have that either, if you don't know, let's put it that way, if you don't know what the actual pressures are, or the equilibrium pressures for that matter, if you don't know that information, then you can still calculate delta G, because we are giving you these pressures, right? But it's not specified whether they are equilibrium or not. Okay, so we don't know. Are these equilibrium? We don't know. So if we don't know, then we take our precautions. So instead of saying that we are going to use K, because we don't have K in this case anymore, then we say delta G of reaction is going to be equal to minus RT logarithm of Q. And what's Q here? Q is going to be the pressure of methanol divided by the pressure of carbon monoxide times the pressure of hydrogen squared. Okay, we have a 2 in front of the hydrogen, so you have to square that pressure. Okay, so that means if we incorporate everything in this equation, then we have minus 8314 joules mole Kelvin times temperature is still the same, 298 Kelvin. But now we have the logarithm of Q, which is the pressure of methanol, which is 1 atmosphere, divided by the pressure of carbon monoxide, which is 0.010, times the pressure of hydrogen, which is also 0.010 but raised to the power of 2. Alright, and when we calculate that, is minus 34.2 kilojoules per mole. So remember to take care of your units here. You initially you get joules, but then I just converted to kilojoules. Okay, so you have 3 different values of delta G because they are calculated at different conditions. So depending on what conditions you will have a different value for delta G. One thing that you can say here is that all the values that you calculated are negative, so all this reaction in this forward direction under all the conditions that you have calculated, it's spontaneous and in the forward direction. Now this question is a little more interesting because we are giving you what the change in enthalpy is for a reaction. It's minus 25.8, and we are giving you what the equilibrium constant for the reaction is. It's 1.4 10 to the power of 3, and we are giving you that happens at that temperature. However, the question is, what is the equilibrium constant for the reaction at 655 Kelvin? Okay, so with this information, we want to know what is the equilibrium constant at that temperature, right? So where do we start? What can we do with this information? You have at this point we've been talking about delta G, equilibrium constant, and now we have delta H, we have the equilibrium constant, and we have temperature. So how do we connect these pieces together? So start thinking about relationships in which you can use delta G with delta H and the equilibrium constant. So the first one that you might think, because that's what we've been talking in this section, is delta G is equal to minus RT logarithm of K. So we have K, we have the temperature, which is 298, and well, from there you can calculate delta G, no problem at all. And what do you know that relates delta G and delta H? Well, we also have delta G equals delta H minus T delta S, right? And how does that help you in any way? Why would you want to calculate delta S? Because here you can calculate delta G, right? And then it becomes that you have delta G and delta H, and you still have the temperature, so you can calculate delta S. Well, the thing is, we need to calculate the constant at a different temperature, and to calculate the constant at a different temperature, we need delta G at a different temperature. And this is the equation that allows you to calculate delta G at different temperatures, right? So that means at some point we are going to set the temperature at 655, and then we are going to calculate delta G at that temperature so that we can calculate the equilibrium constant. But in order to do so, we need delta S, and that's what we are going to, this is the sequence that we're going to follow. First, we are going to calculate delta G, and then with delta G, we are calculating delta S. Okay? So delta G is equal minus A314 joules mole Kelvin times 298 Kelvin times the logarithm of 1.4 10 to the power of 3. Okay, and what we obtain here is minus 17.9 kilojoules per mole. Remember, do the conversions from joules to kilojoules. You don't have to, it depends on what the unit is going to work at the end, but I always convert delta G to kilojoules, right? So if delta G is equal to delta H minus T delta S, then T delta S is equal to delta H minus delta G, and this means that delta S is equal to delta H minus delta G divided by the temperature. Right? So delta S here is going to be delta H, which is minus 25.8 kilojoules per mole, minus delta G, which is minus 17.9 kilojoules per mole, and we divide this by the temperature, which is 298 Kelvin. Okay, and what I get out of this, after doing the proper conversions with the units, I get minus 26.5 joules mole Kelvin. And I want to stress out the joules here. Okay? So now we have delta S, alright? And with delta S and delta H, we can calculate delta G at a different temperature. So that's the next step. At 655 now, delta G is going to be delta H minus T delta S. Remember, we are assuming that delta H and delta S do not change with temperature, which is not correct, but simplifies our lives. So this is equal to minus 25.8 kilojoules per mole minus 655 Kelvin times minus 26.5. Let's convert this to kilojoules. 10 to the negative 3 kilojoules mole Kelvin. Okay? What I get out of this is minus 844 kilojoules per mole. So this is delta G at 655 Kelvin. Okay? Now delta G equals minus RT logarithm of K, which if we are calculating K now, then K is equal to the exponential of minus delta G divided by RT. So how about we calculate this term first? So minus delta G divided by RT is equal to minus 844 10 to the negative 3 joules per mole. And I'm doing that because down here we have 8314 joules, okay, mole Kelvin, times the temperature, and now the temperature is 655 Kelvin. Kelvin cancel with Kelvin, joules per mole cancel with joules per mole, and the number that we obtain here is 155. Okay? Now K is going to be E raised to the power of 155, and this is equal to 4.7. Okay? So the constant went from 1.4 10 to the power of 3 to 4.7. The constant decreased. Okay, the constant got smaller. You increase the temperature and the constant got smaller. Now, does that make sense? Would you expect this to happen? Well, things to pay attention to. The delta H of this reaction is minus 25.8. Therefore, this is an exothermic reaction. And we have said that an exothermic reaction, if you increase the temperature, is like you are adding heat to the products, and heat is a product of your reaction. If it's exothermic, you increase the temperature, you are adding heat, you are favoring the reactants, the concentration of reactants will increase, and therefore the constant will decrease. Okay, so yes, we are expecting this to happen for an exothermic reaction. You increase the temperature, the constant will go down. As a review here, well, it's all about calculating delta G at any other situation. Okay, not always. Well, what we've done in the past has always been assuming that you are doing that under standard conditions, but in real life, not everything. Let's put it this way: hardly everything is under standard conditions, so you have to adjust to whatever conditions you have. And in that case, you use this equation to calculate your delta G under those different conditions. So what we've done in past chapters was just calculate delta G using delta G's of formation, using Hess's law, using delta H and delta S. At that point, we were just calculating delta G standard. Now, for any other situation in which you don't have standard conditions, then you can use this set of equations. If you are This basically is non-equilibrium conditions, and of course if you are at equilibrium conditions then you use K. Okay, and if we are working with equilibrium conditions and now we are incorporating the constant of delta G, then remember that delta G, if it's negative, then forward direction, this means spontaneous in the forward direction. Okay, if delta G is equal to 0, you are at equilibrium, there is no net change, there is no neither one of the directions are favored. And if delta G is positive, then the reverse direction, let's put it this way, spontaneous forward, here is non-spontaneous forward. Okay, meaning that the reverse direction is the one that is spontaneous. Okay, and if you have proper data, if you have thermodynamic data, you can calculate K using just the exponential of the delta G in this case. Okay, so this equation comes from that one. All right.